So the plastic sector in Ireland, it's 179 companies, 6,500 jobs, and a turnover of 1.7 billion. But this is just companies that say that they're plastics manufacturers, but really 80% of all medical devices are plastic. So you can take the vast majority of the 400 companies in the medical device sector as well. And if these are combined, the plastic sector contributes to 33,500 jobs in Ireland and nearly 10 billion in exports. So it's a crucially important sector to the Irish industry. At London Institute of Technology have been training graduates in polymer engineering since the 1970s, and we've progressively grown since then. We started doing research in the 80s, and we're now at the home to Enterprise Ireland's Technology Gateway Centre in Polymer Processing. So this will be a sister centre of the Crest Centre that was just presented. So again, it's very much industry focused. I'll go through that later. To feed into this centre and also to the Irish industry, we have undergraduate training. So if you know people that are interested in STEM or careers, polymer and mechanical engineering is what we're offering at the moment. It's a very good career choice. We almost have 100% employment out of it. IBEC companies and medical device companies, they're all constantly coming to us looking for people. And we just cannot literally get enough people to fill all the vacancies in Ireland. Research in AIT, it's focused around the three centres. So Materials Research Institute, which I'm going to talk about, Biosciences Research Institute, which do work in site compatibility, microbiology, sterilisation, and the Software Research Institute, which looks at cloud security, network and infrastructure, connected and immersive media. Now obviously there is interactions between all of these, which we'll touch on a little bit later. So the Materials Research Institute itself builds on 40 years experience in polymer field. We're based in a custom-built research hub with our major injection molding machines and extrusion machines in engineering and informatics building, and also our apps building comprising 2,500 square feet of processing halls. This is our general structures to give you an idea. So the App Centre is, as I said, an industry-focused centre, as is the Centre for Industry Services and Design. I'll talk about that in a second. But these are underpinned by our basic research in fields such as biomedical, controlled release and smart polymers, polymer process and additive manufacturing, and composites and upscaling. But really, polymer chemistry and polymer processing underpins each one of those areas that we're interested in. So the Centre for Industrial Services and Design, this also ties into our App Centre. What we're dealing with, we've grown from dealing with about 50 companies in 2007 to dealing with 100 companies in 2014. We're working on about 200 projects a year and 29 innovation vouchers, and we did over 30 last year in this centre alone. So innovation vouchers you've heard about, it's Enterprise Ireland funding to do preliminary research. So AIT is actually it's in the top 3 in the country of higher education institutes or authorities for performing innovation vouchers. Sorry, I should say that the majority of these projects are small scale and it's troubleshooting. So polymer companies come to us, medical device companies, or pharma or automotive or whatever. They come to us with a problem, a processing problem. Their line is down, there's something happening, there's a colour coming up in polymer that shouldn't be there. So it's really to troubleshoot that, find out where the problem is coming from, and mainly the question we're asked is it our problem or is it our supplier's problem? So we're able to give people an answer to that question, and then they can go and try and sort it out from there. The design part of the Centre for Industrial Services and Design has been working in additive manufacturing since 2008. Our primary source of funding is actually the Enterprise Ireland voucher, and we've done 130 of them in the last 7 or 8 years. From these, we've managed to launch 24 products, and these are all currently on the market. Our main design tools is Creo CAD system, and we have 3D systems, Vipers and SLA systems, so we can use those 3 listed monomers for making parts. And we also have fused deposition modeling printers, including customized filament production. So what I mean by the fused deposition modeling is you have a filament of polymer and you melt it, and the head moves and it lays down a layer of polymer. So what we can offer is, as well as the standard PLA type materials, we can actually make bespoke filaments. So we have a full production system for making filaments. We have a range of compounders, so we can compound in different additives, nanomaterials, active pharmaceuticals, etc. I may actually have listed that again later on if I have. I won't say. So in terms of our SLA, we do a lot of in-house product design for form, fit and partial function. The big problem with this type of system is you can't get something like a snap fit. The material is quite brittle, so for full function you would have to make it out of thermoplastic. We can make commercial prototypes for medical devices. We've done some work imaging organs and aneurysms. And also, a little bit what I want to talk about later is making of tools for the polymer processing sector. So, again, I knew I had it somewhere. The fused deposition modelling, twin screw compounder, stabilizers, fillers, API, for high tolerance filament production. And we can also compare, so for instance, the dumbbell sample at the top, we've used this to compare it to standard injection moulding. And we're getting about 85 to 89% of the strength of an injection moulded sample by 3D printing. This is purely related to the pressure that's used in injection moulding, as opposed to 3D printing where you're laying it down and it can cool as it wants. So a practical example of using 3D printing for the polymer processing sector. We were asked by a company to look at reducing the blow moulding cycle. So one of the critical parts of blow moulding, a bottle in this case, is the thread design. So this has to be cooled sufficiently before the bottle is expelled from the mould. So we ran a study where we compared existing machined stainless steel versus a 3D printed system with conformal cooling. We ran FE analysis and verified results using infrared temperature analysis. So this shows you what we looked at. So with the standard machined stainless steel, you can see with the inlet on the right, the coolant, which is usually water, heated up considerably once it got to the first corner. If you compare that to a curved system using conformal cooling, which by the way is only possible with 3D printing because you can't machine those kind of curves, we were able to reduce the temperature increase and reduce the cycle time from 14 to 11 seconds. It mightn't seem like a lot, but if you're producing thousands of bottles a day, that saving is actually quite considerable. Hopefully these videos are going to play and I will talk over them. If not, I'm in trouble. So, another project we're running is looking at additive manufacturing to make molds for injection molding. So, if you want to make 1 to 10 parts, additive manufacturing is perfect. If you want to make tens of thousands of parts or hundreds of thousands of parts, injection molding is perfect. But if you want to make, say, 2,000 to 3,000 parts for a medical device that's then going to be validated by a regulatory body at the start of a project before you start making money, that could get quite expensive. So these molds can cost 70 to 100,000 euros and up just to make the injection mold. To reduce the cost of that, some companies use an insert mold, so they have a standard steel mold that you see in a minute, and they just machine the metal insert from the middle. And again, that will do a couple of 100,000 parts, and if you're in an early stage of developing a product, you may even want to change your design once you've seen some molded parts. It's not an efficient way of making prototypes or short runs of samples. So what we've started to do is we actually 3D print the insert for the mold. So this is 3D printed using our SLA Viper system. It will eventually get into a mold. And then we can take this part, put it into a standard steel injection mold, which we have eventually. The last time I tried to skip this, I just messed up the whole thing, so I'm not going to try and do it again. So this is the insert mold. So this recess here is normally where you put your steel. So we have a steel plate that goes into it, and you can see the polymer 3D printed parts there. So again, some of the challenges with this, of course, is you're using a plastic tool in a steel mold and you're injecting in molten polymers at over 200 degrees Celsius. So the challenges are obviously deformation, wear on the tool. They're pretty much the main challenges. Also, if you're making large parts, warpage of the part as it's cooling. So there are certain challenges involved. But for parts like this, we've been able to injection mold a couple of hundred parts. So that was the part in the tool. I'm pushed for time, so I'm going to skip on. And then we can use that tool for injection molding. So this is actually the part in the injection molding cycle. So when the mold opens the next time, you'll see the sprue sticking out of the the mould where the part is actually moulded and it just needs to be ejected then. So we're working with companies who are contract holders who are producing parts for medical device companies with a view to developing this technology for those short runs, for the 2,000 to 3,000 parts, so you can make the parts quite cheaply at the start of your project, send them for FDA approval because you're using the material you want to use and also the system you want to use. The only thing that's going to change is the type of insert. And potentially, if we get this good enough, you could use the same polymer insert instead of the metal insert. I think I'm running out of time, so I'm going to leave it at that. But this is kind of the range of products that we have developed using 3D printing. Some of you may have seen some of them. They've ranged from oil handling systems for oil rigs to the Hurloge. We've also been involved in the Cooltech Hurley, Stylus, Busty Bends, and several other projects. Thank you all for your time. If you have any questions, I'll try and answer.